Hello, my name is Eduardo Gutiérrez. I am a PhD student at the Instituto Argentino de Radioastronomía, and I am also an associate of the Astrophysics Working Group in the collaboration led by Manuela Campanelli. I will present here our latest results on predictions of the electromagnetic emission from supermassive binary black holes approaching merger. So supermassive black hole binaries are expected to be not only the most intense emitters of gravitational waves, so the main target of LISA, but also emitters of electromagnetic radiation. Contrary to most stellar mass black hole binaries, of whom we already detected gravitational waves, supermassive black hole binaries are located in gas-rich environments, namely at the center of merged galaxies. So they could, in principle, present very similar phenomenology to single AGNs, namely accretion disk and also jets. Of course, they will present important differences due to the presence of two black holes instead of a single one. Observers are currently looking for these systems in the electromagnetic sky. They differentiate them into categories, dual AGNs and binary AGNs. We are interested in these systems that are those gravitational bound forming Keplerian binaries. So the key question is how to distinguish non-dual supermassive black hole binaries from single AGNs. And at least one of the answers is to look for specific spectral features and time variability. There are a few candidates in the literature. Besides the famous case of OG287, there are variabilities in the light curves of some galaxies attributed to the presence of supermassive black hole binaries. Two possibilities are Doppler busing by the movements produced by the movements of the holes, and also self-lensing between the holes that some authors propose as an explanation of quasi-periodic eruptions in the X-ray band. The problem is that none of this system is confirmed as a binary so far, and so we hope to do multi-messenger observations in the future, for example, using LISA and Athena together when they are operational. But for this, we also need detailed theoretical predictions on what to look for when these instruments are operating. Our approach to contribute to this field is to do first GRMHD simulations of accretion flows onto closed binary black holes, and then to ray trace the data to calculate images, spectra, and light curves. This was already done by our group in this work led by Stephanie Dascoli in 2018. And this work could only follow 3 orbits of a system of non-spinning black hole. And so here, in the current work, we are extending this to many more orbits and to spinning black holes. So I will not enter into the details of the GRMHD simulations that were performed by various members of our group. You can find more information on this in Luciano Combi's talk in this workshop. I will only say that in this case, we ray traced 2 GRMHD simulations of the accretion onto a binary system at 20 M separation using an approximate space-time for the background, space-time. And one of the simulations is with spinning black holes and the other with Schwarzschild black holes. We use the ray tracing code BOTHROS developed by Scott Noble and collaborators that solves the geodesic equation for arbitrary space-times. It uses a camera to source approach, and in this case, we limit ourselves to the fast light approximation. So the idea is that we put our camera at some far distance from the system, and we solve the geodesic equation. Here you can see the path of these geodesics, and in dark you see the shadows of the black holes, or those geodesics that ends in the black holes. This is a 3D movie of the shadows of the 2 black holes. Over these geodesics, we solve the radiative transfer equation, adopting some model for the emissivity and absorption. For example, if we consider synchrotron emission and inverse Compton emission from the plasma, we obtain these images, this video. Since the GRMHD simulations we use are done in the Collin approximation, we have the freedom of density scale, and we can explore high accretion rate systems and low accretion rate systems with the same data. So we explore two scenarios: an optically thick scenario and an optically thin scenario. In the first case, we choose an accretion rate of 0.5 in Eddington units. We put our camera at 1000 M, and we assume that the disk emits black body radiation from the photosphere, and there is also a corona that emits inverse Compton emission. In this case, we have to restrict ourselves to face-on views because at higher inclinations, the photosphere is not properly calculated because the flow is too optically thick. So these are two images of the flow at different bands. In the left, you have UV radiation and X-ray radiation on the right, and it can be seen that the circumbinary disk is the main emitter in the UV, but in X-rays, the optically thin coronal emission is what dominates. This can be seen clearly in the spectrum on the right, where the different components are differentiated in different colors. In blue, you have the circumbinary emission peaking at UV, and in X-rays, you see that what dominates is the mini-disk emission. A distinguished feature in this spectrum is that the thermal peak is broader than simple black body disk emission. And so in the lower plot, we show that we tried to fit the spectrum with analytical Novikov thermal models. In the left, the thermal peak is fitted by the sum of a thin disk for the circumbinary plus one disk for each mini disk. But in the right, we try to fit the thermal peak with a single disk model, a single black hole disk model. And the conclusion, the preliminary conclusion is that it is not easy to reproduce this broad spectrum with a simple thin disk model. This, what I showed is for a single time, but the most interesting feature of this system is the variability. So I will show you here two movies, one for spinning black holes and the other for non-spinning black holes. So we have 15 full orbits for the spinning case and 11 full orbits for the non-spinning case. You can see that the mini disks in the spinning case are much brighter than in the non-spinning case, and this is because they are more massive. This can be seen also in the spectrum, where the mini disks are brighter, and in both cases you can see a periodicity in the thermal emission of the mini disks, and this effect is caused by a periodicity in the accretion rate, by a filling and depleting effect. So with having 11 and 15 full orbits of the systems, we are able to calculate light curves. So here you have the integrated emission from the mini disk, where you can see more clearly the periodicity I mentioned, and also that the mini disks in the spinning case are brighter. And at higher frequencies in X-rays, the variability is more chaotic, but even more intense. And this is especially true for the spinning case. So going quickly to the other case, the optically thin scenario, we consider an accretion rate of 10 to the minus 5. And in this case, we can explore different inclination angles because the flow is optically thin. What I will show you here is a movie for an inclination of 90 degrees, where you can see this effect of the self-lensing when one of the black hole is behind the other. So we have these peaks twice per orbit because both mini disks are similar in brightness. This effect is highly dependent on the line of sight inclination. So we explore different inclination, and of course the peaks are the brightest for the edge-on case. We also are aiming to study the profile of individual peaks, but we need more temporal resolution to do this, and we are aiming to do that. So finally, let me just emphasize that in addition to the development of the new generation instruments as LISA, Athena, and others, we need to have the best theoretical predictions on what to look for in the data when these instruments are out there. So thanks for attending, and I am open for questions.